All right, so today's topic is electric potential. Now, before we get into the slides, let me sort of summarize this chapter, what the main idea is behind this, this chapter, and then we'll get into the slides, okay? So again, I'm going to summarize this on the chalkboard, or the modern chalkboard, which is the iPad, among other things. Okay, so here's the idea behind this chapter. So let's say you have a bunch of charges distributed. Okay. And what you're interested in is, what is the electric field everywhere in space? Okay, that's what you're interested in. So these charges will produce an electric field all around, and that's what you're interested in. So for instance, the electric field at this location is that, this location is that, and so on. And you can see that the electric field is a vector field, meaning the electric field is a function of space. Okay, for now, we'll won't consider time, but if the charges moved around, if these charges moved around, it would be a function of time as well. Okay, so we'll keep things simple, and we'll say the charges are fixed for now. Okay, so there's the electric field, and so again, what we're interested in is we want to know the electric field everywhere. So you can put, if you wanted to know the electric field there, you put the XY coordinates of that point, and you calculate the vector. And the electric field is the X component of the electric field, which is a function of X, Y, and Z, plus the Y component of the electric field, which is a function of X, Y, and Z, plus the Z component of the electric field. Okay. We'll get rid of this charge. All right, so again, what we're saying is these charges produced an electric field everywhere, and we were wanting to know the electric field everywhere. And you see the electric field is what is called a vector field. Okay, so it is a vector field, meaning there's a vector value associated with every space point. Okay, and if these guys moved around, then this function would depend on time as well. Okay, so to specify this vector field, you have to give three functions of space-time if time was involved. Okay, so you have to specify three functions. Okay, so what this chapter is going to do is it's going to show an easier way of specifying this electric field everywhere in space. Okay, so in this chapter, what we'll do is we'll introduce something called a scalar function. Oops. So this was a vector valued function. This is a scalar function. We are, with every spatial point, we're going to associate a scalar value. All right. And what we'll show in this chapter is that the electric field, which is what you were interested in everywhere, is the gradient of the electric potential. Okay, and that's the punchline of this chapter. So what have we achieved by doing that? So to know the electric field everywhere in space, you can either specify this vector valued function, which involves specifying three functions, or you can specify a single function, single scalar function, and take the gradient of that and calculate the electric field. Okay, so by introducing this quantity called the electric potential, Okay, we have simplified the problem by a factor of 3. Okay, we only had to specify this one function to know the electric field everywhere in the region. And that's the point of this chapter. Okay. All right. Now, I don't know if you guys have seen the gradient function. Many of you might not have seen the gradient function. And what the gradient function does is, and I'll introduce this gradient function later in the chapter. I'll show you how to calculate the gradient function, and I'll show you what it means and all that. Okay, so we'll get to that. But for right now, all I want to tell you is that we are, by introducing the electric potential, we can calculate the electric field everywhere, which is what we are wanting to, which is what we are interested in ultimately. All right, so that's the punchline of the chapter. Now let's introduce these concepts slowly. So let's say, now we'll do little examples. So let's say that there's a region in which the electric field is constant and it's pointing downwards. Okay, now you guys all know, you saw this from the last chapter, that if you put a positive charge, the positive charge will feel a force along the direction. The force is given by the charge times the electric field. Okay, so if a charge is positive, the force is in the same direction as the electric field. If you place a negative charge in an electric field, the force is in the opposite direction of the electric field. All right, so if you place a positive charge here, it'll feel a force in this direction and it'll fall in that direction. Okay, and so this positive charge will fall in this direction, and it has a high potential energy here, just like when you drop a ball. A ball falls from a higher gravitational potential energy to a lower gravitational potential energy. So this will fall in this direction. It has a low potential energy in this direction. On the other hand, if you have a negative charge feels a force in that direction, and so it'll fall in that direction. It has a high potential energy in this direction and a low potential energy in this direction. Okay, so now the potential energies at a given location, the change in potential energy between two positions for a positive charge is opposite that of a negative charge. Okay, and that's not so what we'll do is we'll define a new quantity called we'll call it electric potential. Okay, and so U is electric potential energy. Okay, so the only difference is the word energy between the two. Okay, this is electric potential, this is electric potential energy, and so we'll define change in electric potential as change in potential energy divided by Q. Okay, when you define this new quantity, electric potential, what you find is things become charge independent. And so this will be high and this point will be low. Okay, so electric fields point in the direction of decreasing potential. Electric fields, so I can't finish the sentence here. So, decreasing potential. Okay, so that's what this chapter is about. So we are introducing a quantity called electric potential, which is different from electric potential energy. Change in electric potential is change in electric potential energy divided by charge. And by doing this, this depended between two spatial points. So this U final minus U initial, okay, divided by Q. So what we are saying is this difference between two spatial points depended on the type of charge. And so if you divide that by the charge, you get a charge independent quantity, okay? And that's called the electric potential. And it turns out that the electric potential decreases in the direction of in the direction in which electric fields point, okay? So that's the electric potential. So that pretty much summarizes this chapter. So those are the concepts we're going to learn. Okay. Again, let me restate what we're going to learn. What we are interested in is, so if you have a charge distribution, the charge distribution produces an electric field all around. This is a vector field, meaning that with every point, every spatial point, you're associating a vector. And that's what we're interested in. To specify this vector field, you have to specify three functions, the X, Y, and Z component of the vector field. Now, that problem, it turns out, can be simplified for these situations. So this problem can be simplified. There's a case where it cannot be done so, but I don't want to bring that up yet. Okay. So for these electric fields, what you can do is you can specify a function called the electric potential. That's just one function, and it's a scalar valued function. Okay, and you can calculate the electric field by taking the gradient of this electric potential. Okay, so to specify the electric field, all you have to do is specify this one function rather than these three functions. So you have simplified the problem by a factor of 3. Okay. So here we are doing a simple example. Here's a region where the electric field is constant, and you see that positive charges fall in the direction of the electric field, negative charges fall the opposite way. So the potential energy for positive charges decreases in this direction, for negative charges decreases in that direction. So it depends on the charge, the direction in which potential energy depends. So we want to define a charge independent quantity, which is the electric potential. And if you define electric potential as change in potential energy divided by Q, the charge dependence goes away, and this becomes a charge independent quantity. Okay. And you can figure this out. So the electric potential decreases in the direction in which electric fields decrease. Okay. So that's the gist of this chapter. And all this is contained, all that information is contained in this equation. And we'll come to this equation a little later. Okay, so we'll talk about it in a little more detail. So what the gradient means, the meaning of gradient and all that, we'll talk in a little more detail later on. All right, so I'm going to pause the video right now, stop the recording.